Hello everyone, my name is Ruwaiza and today Ashley and I are considering quinine as our analyte. We will talk about two analytical methods. Quinine, first isolated from the bark of the South American cinchona tree in 1820. It's an organic white crystalline compound with an elaborate IUPAC name, as shown at the bottom of the slide. Analytical chemists get excited to work with it due to its fluorescence and UV absorbance. It has been exploited due to its distinctive properties. For some, it's an effective antimalarial drug due to its extensive medicinal properties. For many, it's beneficial as a flavoring agent in carbonated beverages such as tonic water. The 19th century saw heavy consumption of the iconic gin and tonic cocktail due to its gustatory stimulation. However, it is known that quinine should be avoided by children, pregnant women, and people with metabolic disorders. Presently, there's a worldwide necessity to include the amount of quinine and its possible effects since it's common to beverages. The first method we'll discuss is the atomic absorption spectroscopy. In 1953, Sir Alan Walsh, an Australian physicist of CSIRO, demonstrated the usage of atomic absorption as a quantitative analytical tool. AAS takes advantage of the different radiation wavelengths that are absorbed by different elemental atoms. AAS is used in the analysis of food and beverage, water, clinical, and pharmaceuticals. As illustrated here, atomic absorptive spectra results from the characteristic absorption of electromagnetic energy by ground state atoms. Moving on the right-hand side, we can see the spectrophotometer. Towards the left is a block diagram illustrating the components of the spectrophotometer. It comprises of the lamp, burner, flame, nebulizer, monochromator, and detector. A solution of the quinine sample is placed manually or via an autosampler in the injection valve with minimum pre-treatment. Different samples can be analyzed relatively easily and quickly using minimum skill and high sampling frequency. The spectrophotometer is widely available and is of low maintenance, therefore cost efficient. Now let's look at the details. Firstly, the cathode lamp, which is filled with the argon or neon gas, and the cathode made up of the element undergoing the analysis. Next, the burner, which produces the flame to aspirate the liquid and atomize the remnant solid. The nebulizer, which disperses the sample uniformly as a fine mist throughout the flame. The monochromator selects and filters spectral lines emerging from the lamp using a grating or a prism set at an angle. The atomizer and the monochromator are key to making the AAS work efficiently. The detector is any photosensitive device such as a phototube or a photomultiplier that is responsive to the characteristic wavelength and sensitive to detect the change in radiant energy. Finally, the detector is connected to the computer, which acts as an amplifier. According to Harris 2016, the AAS spectra are obtained as sharp lines. As such, 70 elements can be measured simultaneously in many instruments. Calibration graphs can be constructed, and applying Beer's law, quinine concentration can be quantified as a function of the wavelength intensity. On the downside, atomic absorption spectrometer has been known to pick interferences, such as spectral, due to background radiation caused from other elemental signals overlapping the analyte signal, chemical, due to the incomplete dissociation of other compounds in the flame, ionizational, due to high temperature, which causes a number of vaporized atoms to become ionized. To combat this, most recently, there are latest atomic absorption spectrometers available, such as the Perkin Elmer 5000 and the Pinnacle 500 flame atomic absorption spectrometer. Nevertheless, all types of interferences should be considered. Thank you for listening.
The next method we'll be looking at is HPLC-UV, but first, let's have a brief look at the two methods individually. High-performance liquid chromatography has over the years been the most widely used type of elution chromatography. Early methods used glass columns packed with lengths of particles that were coated in a liquid which formed the stationary phase. The solvent is then forced through a particle-filled column, achieving high-resolution separations. A typical HPLC uses two columns to perform the analysis, an analytical column and a guard column to prevent contamination. The stationary phase is often polar, whilst the mobile phase is nonpolar. In the 1930s, photoelectric transducers were introduced for UV-Vis radiation, and by the 1940s, the modern instrumentation for absorption spectroscopy became easily available and has since had much progress. Typical UV spectroscopic equipment consists of 5 different components. These are a source of radiation, a wavelength selector, one or more sample containers, a detector, and a signal processor and readout. The simplest method for UV absorption is a filter photometer. It is a single beam instrument that has a single path between the source and the detector. However, double beam instruments are usually preferred over single beam due to the stability of the infrared radiation. HPLC-UV allows for extraction of quinine from the cinchona bark, providing a method that is fast but also providing data for processing of quinine on a large scale from raw material. The method includes UV detection for this analysis of quinine, which contains UV absorbing properties. This then allows for the correct determination of wavelength in order to complete the HPLC. The technique only requires 50 milligrams of cinchona bark, providing a method that is less complicated, more convenient, and more precise and accurate. Providing a 2-in-1 method, cutting down time compared to using the machine separately, the method is simple, quick, and selective. It would be useful not only to determine quinine, but also provide information that would help develop the extraction technology needed to process quinine. Advantages for AAS are that it is simple, quick, and inexpensive. This is crucial for quinine, as most countries that have prevalent cases of malaria are often third world countries that cannot afford expensive equipment. Other advantages such as ease of use, sensitivity, low amount of sample needed, and high sampling frequency all contribute to why AAS is still used to quantify quinine today. The advantages of HPLC-UV are its excellent precision and accuracy, which is vital for a drug that is still in high use. Its low concentration sensitivity is also useful as only a small amount of product is needed. It is also insensitive to any changes, be it chemical or physical, and hence it is interference-free. Disadvantages of AAS are that compared to HPLC-UV, its precision and accuracy are much lower. This is due to the interferences that can occur whilst quantifying the analyte. Chemical, ionization, physical, and spectral interferences are able to affect the results of the analysis. The disadvantages of HPLC-UV are that because it's a newer technique, the equipment would be more expensive than the AAS method, as most labs would already have this. It is also more time-consuming due to the 2-in-1 method and would require training and more skills to operate. So which method is more effective? There is no fully effective drug for malaria yet, however quinine is still the most commonly prescribed anti-malarial drug. Techniques used to quantify quinine need to be extremely precise and accurate to ensure a dose of the drug that is neither too potent or not potent enough. As malaria is still a disease that concerns the HWO, with 228 million cases and 405,000 deaths worldwide in 2018 alone, the need for antimalarials is still high. The analysis to quantify quinine therefore needs to be cost-effective, as the amount of drugs produced would still be high, with most of those going to third world countries that struggle to afford basics. Therefore, the method chosen today to effectively quantify quinine is HPLC-UV. As even though it may be pricier than AAS initially, the efficacy and precision of the method far outweigh the cost.